So we're going to get started with a little definition first. I want to describe what digital signal processing actually is. So our definition is the use of mathematics to modify an information signal. A good way to understand this is to first go through some of the use cases, why you'd want to use some of this. So I like to break this into two basic categories. One being for getting data. We're going to process our signal in order to get data. Or we can modify our signal to actually produce a new signal or change the signal, the output from it. So some examples maybe of getting data. We can get the data about the signal itself. So for instance, we have like an audio signal. We're going to get amplitude peaks from it, and maybe we'll visualize those or do something like that. We can also get data about the environment through which the signal moves through. An example of this is sonar and radar. The other side, the modifying of the signal, we have a couple examples. We might have output modified version of the signal itself. So when we have a guitar plugs into a reverb effect pedal, we actually modify that signal, and then that actual signal, we're hearing the differences there. We can produce new signals. We can synthesize speech from a text signal, which is actually splitting off after processing it and creating a whole separate signal. So I'm going to go over a couple more terms here so that we can build up to this. We have a sinusoid, which is really just a sine wave here. Basically what we're doing here is we're graphing a sine wave across, and this is over time. So we have our highest point here. Vertically, we're going to be graphing amplitude. So we're going to have positive numbers up top, negative on the bottom, and this is over time. So we see our peaks and our troughs. Troughs are obviously going to be the lowest point, peaks are the top points. I'm going to explain amplitude now. As you see, this is our sine wave once again graphed over this. We'll see time increases as we go to the right, and then up and down we still have our amplitude. And it's going to show us basically our loudness, is basically how we're going to perceive that. We have a concept called magnitude, which we're going to see when we graph in a different domain, which we're going to get to when we graph frequency instead of time. Basically a good kind of cheating way to look at this. It's not the most accurate, but the way to just get a good idea of it is to think of it as amplitude, but only the positive values, because that's all we're going to show on the graph. And finally, we're going to get to frequency. When we talk about frequency, we're going to be talking about the rate of repetition of events over time. Now, how this is going to appear to us when we're talking about audio signals is it's going to sound like the pitch is changing. We're going to hear it as as the frequency gets more rapid, it's going to go up higher in pitch for us. So we need to talk about the Fourier Series. This is kind of the basis of most digital signal processing, a lot of what we're going to focus on today. Jean-Baptiste Joseph Fourier, which we have a picture of right here, came up with a kind of crazy idea at the time that any waveform, this is any sort of signal of information, can be basically broken down to the sum of as many sine waves as you can take to make it. So we can start with one sine wave and through additive synthesis continue adding to that to create this full signal. This is really important for us. So with digital signal processing, we're going to try and take that whole signal, tear it apart, or build it. So we're going to explain the time domain now. So there's two main domains that we're going to be talking about today, the time domain and the frequency domain. Time domain is very much like we showed before with the sine waves. This shows our samples, though. So this is really a bunch of sine waves mixed together, basically. Is a very basic example of it. So this is our samples, graphed once again over time and with amplitude up here. We're going to get the frequency domain here. So now what we see in this graph is we have our magnitude on the left side here. This is going to be our loudness also perceived. All the way to the left, we're going to have our lowest signal. So we're going to start around 220 frequency, and then we'll rise up from there. So our higher pitch frequencies are going to be all the way over on the right. So in order to switch between these two domains, so we can visualize them, so we can operate, maybe there's some things where we can operate in the frequency domain. It's a little bit more efficient. We're going to need the Fourier Transform. So the most simplest idea, the best way to look at this, is from taking that time domain samples into the frequency domain. And remember what we said before about the Fourier series, in that this is really just a bunch of sine waves making up this one waveform. So I have a visualization here that I've pulled from Wikipedia. It's one of the best visualizations I've seen for the FFT. And so you can see here, we have our main waveform, which is graphed over time. And we see it's broken up into all these individual sine waves right here. We're going to kind of set it to the side so we can visualize this. And we see each individual sine wave. You see how we have the biggest sine wave right there, the first one, is the tallest. That means it's going to be the loudest. Now we have the frequency domain. So we have the lowest signal, it's going to be louder. We go, as we increase in frequency, they get a little bit lower. So this sound is going to be more of like a thicker, deeper bassy sound. So we'll go through this again. This is the waveform over time, split it apart into sine waves, turn it on its side, and then we're going to be able to see our individual sine waves, and then flipped over into the frequency graph. So, all this to tell you that we want to be able to use some of these things in the Web Audio API. I don't know if some of you may be familiar with the Web Audio API. It's been around for a little bit now. Most of the things we've been using it for is a little bit in games, and mostly like kind of toy apps, which is unfortunate. I'd really like to see some more real work done with it, but we're getting to that point. There's going to be a lot of updates coming to the Web Audio API. So we're using this for, like I said, synthesizing audio, creating oscillators, passing them through all types of like delay nodes and these types of things and effects. And we're modifying those signals, and we're scheduling sounds. Scheduling is a lot of what we're doing in games. So if we want to go over a really quick high-level usage of this, we'll go ahead and step through a little function that we've written here. So we look here, and we have a function called frequency. We're going to pass our frequency, function called play note. We're going to pass in frequency. So first thing we need to do, we need to get an audio context, and we get that straight off of window. This is going to be our basis for what we build we get all our classes and things from. So we get our audio context first. You generally want to have one per session. So like if you have a program that's going to be running on this, you only need one audio context. No reason to really work with more than one. So first we're going to create our oscillator node. That's going to be our source node. That's where we're going to get our signal from. We're just going to start generating our signal from there. We're going to create a gain node so we can affect our loudness right there. We're going to go ahead and set our gain node all the way to 1, this is between 0 and 1. So we'll set it to 1, that's like saying 100%. We can set the wave shape to triangle for the oscillator node. We're going to set the frequency to what we passed in, which right down here is 440, connect it up to the gain node, connect the gain node up to the destination, right? So the destination, I have not explained yet, is basically just going to be our speakers. So it's going to be our speakers, our headphones, anything like that. And then we're going to start our oscillator. So probably the most confusing part about this API for me, it was trying to visualize this audio graph that we have to set up. The audio graph is where we're connecting up to each of these nodes. We're connecting up chains. So we want to try and help visualize this. Firefox released a thing a little while ago that is the web audio inspector, right? We have the web audio editor. So each time that we create these types of nodes, we have our oscillator, we see where it's connected to the gain, and then connected to our destination, which is going to be our speakers here. So I've come up with a little demo. I went and took a project that I found, it was called Streams Editor, and on the train up here, I went and forked it and made it work with our Web Audio API here. And I'm going to go ahead and show you all this really quick so that we can, oh, sick, it doesn't work in Firefox. I'm not going to show you all that. Yeah, so wrote these slides in Chrome, and then some things broke this morning, so I thought that Firefox was my saver this morning, but we'll come back to that. So basically what that would have done is created these nodes, and you can plug them together. We'll be sharing the link after the talk so that you can play with these things. Moving on, though. So we want to talk about our analyzer node. This is another node that we'd be hooking up into that chain. It'll be running, like I said before, the discrete or fast Fourier transform over our signal, allowing us to get data in the time or frequency domain. What analyzer node actually does is goes in and samples our signal in real time, and will give us the stuff in the time domain, or if we want it to, it'll run that transform over it and give it to us in the frequency domain. So let's run over the quick API from this really quick. If you don't retain this, that's like totally fine. These are going to be up, and there's a lot of good resources about this. Just want to kind of step through as like a basic understanding. So once again, we have our oscillator node. We're going to create an analyzer node this time, and we're going to create a new thing that we haven't talked about yet. We're going to get to it on the next slide, but just for now, it's called a script processor node. Then we're going to set up our little uint array right here, which is an empty array. It's going to be data, or fill with zeros here. And we're going to set that to the frequency bin count, kind of arbitrary for these purposes. So we're going to connect our analyzer node up to our processor node. And we get this event here, on audio process. In that process, this is where we're actually going to be able to use our analyzer node. In here, we can get our byte frequency data. It's a little bit different of an API. This was a kind of confusing thing for me. Also, last time when I gave this talk, it was a little confusing for people. So this array is there's so many elements in it that we're not going to be able to use it the same way that we use most like APIs in JavaScript, where you just call the method and it returns a copy of the array. We actually need to pass in our array, and it's going to fill it up for us synchronously. And then right after that method call, we're going to be able to, I don't know if you can see the comment over here, but we'll be able to loop over all of this data and either draw to canvas, use Three.js, use WebGL, any of these things. This is where we do our visualizations. So this is run on audio process. It's good to think of it as something that is going to run kind of like very similar to like on a request animation frame, something that's going to be just called rapidly. So you don't want to do like crazy, like you want to do crazy things in there, but you want to do it efficiently. Then we're going to do our analyzer node. We're going to connect it up to the oscillator. Processor node connect to the oscillator, and then we're going to start that. And now when we set up our oscillator node, if we were doing that triangle wave, we'd actually see that triangle updating right on canvas if I was rendering it here. So have an understanding of the analyzer node. We'll go over the script processor node real quick. Like I said, we have that on audio process event, and there's a couple downsides to it, right? You have to write it so that it's contained within your regular code. It's hard to reuse. It's not the best situation right now, is basically what I'm getting at. So we want to do some examples of what I'm actually talking about when I want to visualize this stuff in 2D. So we have our we're going to be visualizing the the time domain in real time. We're going to be visualizing the frequency domain in real time. And we're also going to graph out our entire waveform using the time domain data. So we have an example right over here. So I'm going to go ahead and load some audio. As you can see, we're using that web audio inspector right here so we can see our graph. See, we have our destination. We haven't loaded our sound yet. So it's going to change once we get this loaded in. So we have our destination, we have our analyzer, script processor, and then now that we're loaded in here, we have our source, we have our gain node, and then we go over, split off, and we do our two analyzers. This is where we're going to do our drawing, and then we have our audio destination here. I'm going to turn the volume on. Hopefully it's not too loud. Oh, sick, I didn't plug it in. Yeah, so I'm just going to turn this up really loud and hope y'all can hear it. So basically, we have our time domain right here, graphed over time. This is our main wave. And then we have our frequency domain. As you can see, it's flipped over on its axis. And we have our lowest points of frequency right here and our highest go over here. And then finally, we have our waveform. And we're going to be tracking that progress across it as well. So this is graphed the entire duration of the sample. Here we have our frequency domain. And back in our time domain right here. Go ahead and turn that off. If anyone's interested, this sample is actually from a really incredible composer called Else Marie Padet. She was a Danish composer, I believe, from around the 40s. She resisted in the World War II, and she's just an incredible person. You should definitely read about her. Probably one of the most influential people in electronic music from that early on. So we'll switch back over to this over here. And we're going to go over a new thing. This is what the really exciting part of this talk is. So we have a thing coming to the Web Audio API called the Audio Worker node. So what this is we get to create, much like we have already, a web worker, but we get it with an audio context. So we can clean up a lot of the weird code we have around this script processing things, and we can hopefully make things reusable. So like I said, it's very similar to the web worker. This runs in its own process, so we can be a little bit easier with like our processing. It doesn't block our main thread, right? And then we can create these custom nodes. Hopefully we can, just put them up on NPM and make them so that everybody can reuse them. The current way that all these things are happening is that you have to write everything in your own kind of file. It's kind of hard to reuse. Everyone's making their own abstractions around, whereas this isn't a good enough abstraction that we can just use it on its own, I would say. So let's make a little web worker ourselves. Let's go to the API. We have here, we go do new audio worker node context, and then we're going to pass to this string right here is a file. Is a link to a file. So we have our bit crusher worker right there. We're going to go ahead and set our bits to 8. We're going to set frequency up here to 0.5. And then in our separate file right here, we can have local variables, and we have our onAudioProcess method. And that's what we're going to export right here. So we're just going to loop over all this data that we're going to pass in our either frequency data or our time data. And we're just going to be able to do all our processing right here and then spit it back out, right? This will be the type of effect where we'll actually modify that signal. So that's a good example of what we have here. And we will we'll communicate with this to the main thread the same way we do in workers currently by message passing. So that's an example. There is a shim currently. It's the audio worker node. It was working great until this morning, of course. So I'm not going to be able to show that to you, unfortunately. I would like people to start using this shim as soon as it works again. I'm going to try and make a pull request to it and make it work this afternoon. Because I would like for people to start making these effects, making these different visualizations in a very reusable way, and be putting them up on NPM. So we'd like you to use audio workers. Use this shim right now. There's no reason not to, except for that it doesn't work. Besides that, there will be no reason not to once it starts working. Gosh. So that's what I'd like us to do. I'd like us to have a community effort here. So I feel like there has been a lot of good, very smart people working on these web audio things, but it's kind of scattered all over the place. It's all over GitHub. It's all in just like giant files. There are things on NPM, but it's hard to get them to work together. So I've put together a little bit of a supposed to be helpful example here, which is going to be web audio modules. I'll show that in a minute. And it's basically just a GitHub repository where we are putting all of these together. I don't know if you've seen, there's a GitHub user, Hugh SK, and he put together a repo a little while ago called Game Modules. And basically what it was it had all the kind of small modules and little frameworks that you can find on NPM all in one place. So you can kind of see like the good trusted modules. And it's a good place to start. Because we all know that there's problems with discoverability on NPM. There have been, and they're getting better and better. But these kind of lists like this have been extremely helpful to myself. So I'm hoping that they'll be helpful to y'all. I still have a lot of things to add to it. Right now it has a lot of my modules. I'm not trying to skew anything in that way. There are a lot of other good people's modules. So I'm definitely going to be open to pull requests. Very happy to see that. We have our audiograph editor that I was attempting to show earlier, only used right now in Chrome. And then we have a project called Open Music that's been doing some really, really neat things, especially with, we have like web components that are wrapped around these as an abstraction. If you're interested in talking to me about any of these, building these kinds of abstractions, maybe building like a kind of node streams API, any of these ideas you have, please bring them to me. I'm in a channel called Boring Engineering, is where I do like all my web audio stuff. Nobody's in there but me. I just created a channel, so hopefully y'all join it and talk to me about it, because I'm lonely. And then there's the main. We do have the main channel, Web Audio, where you can talk to Chris Wilson, one of the main people that are working on the web audio spec. He's always been very nice, very helpful with these things. So thank you. These are a couple different things you might want to check out. You can contact me as Jason Voorhees on Freenode, me and Dave 2020 on Twitter, etc. These are all kind of the web audio type things. So, yeah, thank you.